Hello everyone, I'm Siva and I'm going to talk about our tool GRoot, a proactive verification tool for DNS configurations. This work is a collaboration between Ryan and Behmas from Microsoft Research with my brothers Todd and George and me from UCLA. DNS, the domain name system, as most of us are aware, allows users to connect to online services through user-friendly domain names by translating them to IP addresses. As such, any misconfiguration in DNS can lead to service disruptions, as is evident from the recent Azure global outage. Microsoft Azure suffered a global outage due to DNS as some of their users were unable to resolve names related to database and storage. In addition to these services, other Azure services which were dependent on services hosted on database and storage were also in turn affected, so this had like a cascading effect, and the impact lasted for around 20 hours due to caching and other effects. You'll be surprised to know like what led to such a huge outage. It was just a one line of incurred configuration change during migration. To know why this could have happened, let's take a look at the current practices to manage DNS configurations. The general and easy approach used today to check for DNS correctness is black box testing. In this approach, the engineer of an organization has a list of properties that the DNS configs has to satisfy. Let's say as an example property that all queries under their domain should not be rewritten. It is common in DNS for a query to be rewritten to some other query before it is resolved to an IP address. So the engineer for some reason does not want that to happen for any of their queries. So he tests this property by sending some queries to the live DNS system, and the system replies with some answers. All the answers look fine for the engineer, and he concludes that it is fine overall. The major problems with this approach are that it can only find errors after they are live in the system, and it's not an exhaustive process. The engineer might have missed testing a query which probably violates this property. The second approach used by some of the organizations today is configuration review. DNS experts can be asked to review the zone files before they are put into the production system. The drawbacks to this approach are that it is not an automated process and is prone to human errors. So, what would be an ideal situation and an ideal tool to manage DNS configurations? The ideal situation would be a verification tool that can take the DNS configs and properties as input and either certify that the property holds or provide inputs that violates the property. But there is no such verification tool that exists today for DNS configurations. As our contributions, we present GRoot, the first proactive verification tool for DNS configurations that can verify if a property holds for all DNS queries. Other contributions to our paper includes an algorithm to generate query equivalence classes to cover all possible DNS queries in a scalable manner, as there are too many queries to enumerate. We are also the first to present a formal model of DNS resolution that we developed from RFCs that can be used for automatically checking zone files. We also show a way to symbolically execute the equivalence classes that we generated using our formal model semantics for property checking. In our paper, we also prove that our equivalence class algorithm is sound and that for any two queries in an equivalence class, the DNS resolution is the same. Our approach is also complete as we cover all queries since each query belongs to at least one equivalence class. GRoot revealed around 109 bugs on campus zone files and 160K black holing issues on the infrastructure service provided zone files. And more details in the later slides, but first let's take a look at the end-to-end design of GRoot. GRoot takes as input the configurations which are known as zone files in DNS terminology and a property of interest to the user. A simple property could be that a particular domain name like ucla.edu has to always resort to this particular IP address. The more interesting properties are those that have to be satisfied by all queries. For example, all queries must return a consistent answer. It is common in DNS to receive the information for a domain name from different servers, so the operator wants to ensure that the user gets the same answer irrespective of the server that he contacted. Or the other property could be that we saw earlier, that no query rating during the resolution process. Given this property as input and a zone files as the input, GRoot either says that the property holds or provides counterexamples that violates the property. To verify if a property holds, one can enumerate all the queries and check the property for each query. And a query in DNS is a domain name like ucla.edu and a type like A for IP record, TXT for text record, and so on. But to enumerate all queries, there are too many queries as a query can be up to 254 characters and there are like 10 to 15 types. So how does GRoot check the properties efficiently? As said earlier, GRoot generates query equivalence classes. So let's take a look at the GRoot internals to see how GRoot generates these equivalence classes and checks properties. GRoot first checks the zone files and constructs a graph which we call label graph, which is basically the union of all the domain names found in the zone files represented as a tree. And we also add some special nodes and edges to account for the challenges that arise from wildcards and rewrites. Please see our paper for more details on these challenges. GRoot uses this label graph to generate query equivalence class. A query equivalence class is a set of queries that have the same behavior in the DNS. And each equivalence class is represented by a symbolic query. A symbolic query is like a representative of that equivalence class, and these queries are symbolically executed. Our symbolic execution algorithm builds an interpretation graph for each equivalence class, representing all non-deterministic execution traces that are possible in DNS for that equivalence class using our formal resolution semantics. A key insight that speeds up the verification is that the interpretation graphs can be built in parallel as the ECs are independent. And the other one is that multiple ECs with the same name but with different type can also be combined together and built as a single interpretation graph. The next step after the interpretation graph building phase is the property checking phase. A property phi is represented as some graph property. For example, all the leaf nodes have to satisfy certain criteria, or all the paths from root should not be of length more than 5, and so on. Another insight that allows parallel processing is that property checking is also local to each interpretation graph. So the graphs can also be checked in parallel. Finally, the graphs can be built in parallel and also checked in parallel, speeding up the verification process. We applied GRoot to the zone files of a large university. The zone files are managed in a decentralized fashion with departments managing their own zone files. We obtained the campus zone file and 895 subdomain zone files using zone transfer. There were in total 120k resource records, of which there were 4000 CNAME records. The results after checking properties through GRoot are as follows. And GRoot took only 7 seconds on this dataset. The violation of properties in the first table are functional violations and are considered bugs, while the properties in the second table showcase GRoot's ability to help operators explore and understand the behavior of the DNS configurations. Violations of these properties are not necessarily bugs, but are interesting behaviors that an operator may be interested to examine. Let's take a closer look at some of the bugs. There were 49 delegation inconsistencies where the NS records did not match between parent and child zone files, and 9 cases of latent delegation as some of the NS records were pointing towards a web server instead of a DNS server. These bugs affect the visibility and redundancy of the zone and also increase the query response time. When asked, the operator said that to check if a name server is working properly, they directly use the IP address instead of the name, so they never caught these issues. As said earlier, operators can use GRoot to explore properties to understand their configs better. For example, GRoot found 24 cases which are rewritten more than twice, and an operator can inspect these cases for correctness and be guaranteed that these are the only 24 cases possible that are rewritten more than twice and there are no other cases. We applied GRoot to the internal zone files of a large infrastructure service provider, and the CNAME records dominates these zone files. When applied GRoot, GRoot revealed around 160k black holing issues. When asked, the NG replied that this is due to incomplete decommissioning of hostnames that are no longer in use. So there is a lot of craft lying around in these domains which has to be cleaned up if they want to repurpose these domain names. The related work includes the testing and linting approaches from both industry and research, which perform black box testing from multiple vantage points. We have already seen the limitations from these approaches. And there's a large body of work on verifying the network routing layer, and researchers have proposed numerous techniques to perform such verification generally and efficiently. There are some superficial similarities between routing and DNS, but the specific details are vastly different. For example, the packet equivalence class generates algorithms like Veriflow that uses tries and atomic predicates that uses BDDs are not suitable for DNS, since Veriflow does not support rewrites and atomic predicates is expensive with quadratic number of predicate intersections. GRoot can generate equivalence classes asymptotically faster than these approaches due to the hierarchical structure of domain names. That is, GRoot leverages the common prefixes of the queries. Finally, to conclude, through our paper, we presented GRoot, a tool for verification of DNS zone files and a formal model of DNS. Using GRoot, we found 109 bugs in the live DNS zone files of a campus network and 160k black holing cases on the zone files of a large infrastructure service provider. And our tool is publicly available on GitHub, and feel free to contact me on this email address. Thank you.
Great. Thank you, Sarah, for the excellent talk. So we're going to start with questions. We have multiple questions coming on Slack. The first one is, how do you know whether the generated equivalent class is correct? Does it depend on the server implementation to check whether certain DNS flags are implemented correctly?
No, this is independent of the server implementation. This is with respect to the domain names that are present in the zone files. We argue that the equivalences that we generate are correct. And if the server implementation is wrong, then it affects the way that the interpretation graphs are built. So the bugs in the server implementation shows up in the interpretation graphs.
Okay.
We don't actually, so to extend more, we don't actually send the queries to the live system. This is all done statically using our internal model of the RFCs.
Yeah, so the next question is, how do you compare DNS verification with low-level network configuration verification? Would some of the control plane verification techniques like Minesweeper could be potentially used to verify DNS, or is there some new challenges in DNS layer?
Yes, as I said in the related work, if we make Minesweeper closer to use of BDDs and SMT solvers, then it becomes unnecessarily expensive, as there is a lot of structure in the DNS that you are throwing away to just use SMTs. And as I said, atomic predicates is similar. And if you just use atomic predicates by itself, the BDDs are so expensive that the intersection becomes unnecessary. It's the same with Minesweeper also. You will unnecessarily use the SMT logic rather than just using the hierarchical tree of the DNS.
Mm-hmm. Okay, thank you. So we have one last question, and for all the remaining questions, I'm sure Siva is gonna answer all of those on Slack. So the question is from Praveen from Cornell. His question is, how do you handle incremental changes in configuration and policies?
Yes, we are currently still looking at how do we change the equivalence classes on the fly to adjust for the small record insertions and deletions, and we are still looking into it. This is for just one snapshot. We haven't done the incremental version of the snapshots yet.
Okay, great. Yeah. Congratulations on the Best Student Award again.
Thank you very much for a really great talk, and congratulations again on the award.
Thank you.
One other thing I wanted to point out, actually, your paper also received some artifact evaluation badges, which is fantastic. It's great to see work like this where folks are actually releasing the artifacts so others can build on and extend their work.
Thank you.
So we have some questions from Slack. I see you've already answered, but let's do it on video as well. Okay. So from Samuel, how many equivalence classes are generated for a typical property in your experience?
So if there are n records, generally the number of equivalence classes generated is order of n if there are no dnames. But if there are dnames, it will be slightly more, and which is a significant reduction when compared to if you just enumerate all the queries as I showed in the slides, it will be sum of all the 255 character possible queries. But if you use our approach, you can generate almost order of n equivalence classes if there are n resource records in the zone files.
Okay. I have a quick question about the formal model. This seems like it's really cool to see things that were previously specified in RFCs get actually mechanized in some sort of logical artifact. Can you tell us a bit about your experience developing that formal model? And I'm also curious if you did any validation besides the evaluation in your paper to make sure that the model you had, captured what was intended in the RFCs.
Yes, that's a good question. I think that's where we had a lot of time spent trying to figure out whether we have translated the model from the RFCs correctly or not. And we haven't mentioned it anywhere, but I have tried some actual queries to the bind system and saw that whether I will receive the same answer as I expect from my format model. But we haven't written it anywhere or shown anywhere that we have did this evaluation. We did some part, but we haven't done complete end-to-end test on the format model. Great. So the only way that we saw was to test with a live bind implementation or some other implementation of DNS.
And anything especially tricky or novel or interesting about the model itself?
What is it?
Anything especially sort of interesting about the model itself as you were?
Yes. I think I don't know, it's a little hard to explain because there are
tricky cases which involves this D names, wildcards, and like C names and the NS records. There is a interplay between all these 4 kinds of records of what rule will apply when and what rule will not apply when, and like what happens when there is an SOA record and what will not happen when there is an SOA record. So all of these are like special cases which are like hidden in what single lines in the RFCs. Like if you don't misreading that line, then you'll completely generate a wrong answer.
Great. Looks like we have time for maybe one more question on Slack from Elon. Can you say a bit about the running time of GRoot? And does it have a limit on the number of rules or zone files?
I think in the paper we show that GRoot was able to scale linearly with the number of resource records. The largest domain that we tried was around like 20 million records, and it took around like 2 hours, I think, as far as I remember, on this data set. So it's just a linear increase with the number of resource records.
Great. Maybe I'll ask one more quick question.
Sure.
It sounds like you worked with some DNS operators, at least in the campus setting. What was their experience? What was their feedback on a tool like this?
Like I think they were very welcoming, and they're like, somebody even said that, oh, you are the first person to even care to look at these zone files which were lying around for so many years, and many of them responded positive and were willing to share their experiences and try to figure out and fix this stuff. I think most of the stuff that I mentioned in the paper has been cleaned up, at least in the campus setting.